So thank you very much for the introduction and also for the opportunity to present to you Environment Canada's work within the hydrologic, hydraulic, and sediment transport modeling in support of JOSM. What I'm presenting is the work of numerous researchers that you see here, so I'd like to acknowledge them that I'm presenting their research, and hopefully I do a good job with that. The people on the bottom are our main modelers. Myself, I deal mostly with sediment dynamics within the Athabasca system. So, why are we doing modeling? Well, in JOSM, it was identified that there was a need for a more systematic and comprehensive quantification for the modeling of the source, transport, and fate of substances and the associated chemical substances within the lower Athabasca River. So to do this, an integrated modeling framework was set up, and this constitutes two items. And that is, one, we do 1- and 2-dimensional models that I'll explain what those are in a moment, the difference between 1- and 2-dimensional, and the hydrodynamic sediment contaminant substances, the transport and quality simulations within the lower Athabasca River and its tributaries. We also developed a hydrologic model for the entire Athabasca basin because we need to know what flows are coming into the lower Athabasca, and this was done by coupling climatic and hydraulic models. So the overall integrated modeling framework we can think of as an umbrella of multiple components. Within each of these components, we gain information that comes together into the integrated approach so we can better assess what's going on in the Athabasca River, the lower Athabasca. This includes climatic modeling, hydroclimatic, watershed hydraulic modeling, hydraulic, transport, and water quality modeling. So this is the routing of the flows, sediments, associated substances down the river. And this, of course, will be influenced very heavily by the ice regime of the Athabasca. It's a northern river. It's covered for 4 to 6 months of the year. And also the sediment dynamics within that system. So integrating all of that information allows us to make projections on the flows, look at extreme events, sediment contaminant transport, and water quality regimes, and look at how these may change with time. So what is a 1 versus a 2-dimensional model? Models are highly computationally intensive. Some models could take days to months to run depending on the model that you're running numerically on the computer and the data set that you use. We use the 1D model because it allows us to look at long ranges. So in this case, we were looking at a 2-kilometer reach from Fort McMurray down to Old Fort, essentially to the Athabasca Delta, entering there. And with a single D model, we're looking at the spatial dimension along the distance of the river. So if we take variables like depth or velocity, these represent single values or averages across that cross-section. So we're able to look at the change in that value as we move downstream or with time. Conversely, when we use a 2-dimensional model, it's much more computationally demanding, and we tend to use this in smaller areas, and I'll give an example on the Athabasca upstream and downstream of where the Steep Bank River comes in. But here we're dealing with much more variabilities. In the data set, we can look at things in the transverse direction and look at the vertical averaging across with those parameters, and therefore we're able to look at the change in the parameter downstream, but also across the river as well in 2 dimensions. Now, whenever we're dealing with river modeling, one of the most important things to understand is the sediment dynamics. And it's been brought up that many, not all contaminants, but many contaminants have a high affinity for the particulate phase, particularly that fine fraction of silts and clays. And so it's very important that we understand how this material moves through the system. How is it eroded? How is it transported? How is it deposited? And we do this by using a flume, which I was intrigued by Dr. Watson's little flume, essentially, where he could create shears with air. In our flumes, we create shears, bed shears, with the flow of water. I won't go into the details of the flumes. If people want to talk to me about that afterwards, I'd be happy to do that. But we use these flumes so that we can determine numerically and apply these values that we achieve into the 1 and 2D models. And what do we want to achieve? We need to look at how much energy is required to mobilize that material into suspension and any associated substances with that sediment. We also need to look at how much energy needs to be in the water column to allow that sediment to deposit out as well. So these tie into the 1 and 2D models. We've done this on the L's in the Steep Bank River, and I'm using L's as an example here. These are interesting rivers like many of the tributaries in the Athabasca itself. They cut through the Fort McMurray Formation, which, as you know, is the geological strata that constitutes the oil sands. This gives this sediment a very interesting properties. And if we see the graph on the top right, what we've done with our flume is we've placed 300 milligrams of Ells River sediment in Ells River water, and we've spun the flume, and then we've reduced it down to a very low shear. It's practically quiescent, practically still. And we see that after 8 hours, we still have 30% of the sediment is in suspension. Every river I've looked at in the world, if after 8 hours, I'd pretty much have a clear water column. So why is it that the Ells is different? Well, when we look at it and we think about where it's coming from, it is highly hydrophobic. If it has a natural oil content, which a lot of the sediments coming out of these rivers do, oil and water don't mix. If you have sediment coated with oil, it's going to be pushing against, trying to get away from that water. It's pushing against the molecules. It could be going up, down, all around. So it really doesn't settle very well. So we were very interested then to model how this sediment actually moves through, in this case, the Ells River. And we've modeled that sediment movement from the ramp gauging station S45, 40 kilometers downstream. There's numerous variables that you need to apply in many of the models. I won't be giving any specifics about models. I can speak with people afterwards just because of a time constraint. And what we found when we looked at this sediment movement through this 40-kilometer reach was numerically, from the engineering of what it would say should happen, it says that there was enough energy within that Ells River to maintain all of the sediment in suspension. We know that's not the case. Models are not perfect. They're far from perfect. We know that because when we're out in the environment and we're walking in those rivers doing benthic community sampling, fish sampling, whatever, we see that there is cohesive fine sediment in that matrix of the bed and on the surface of it. So we need to work with the models and try and create them so that we can get something that we feel represents reality and calibrate back to that and confirm that. Because what we think has been going on here is that as the water with the sediment moves through the system, it's actually going down into the bed as well. The bed acts as a filter because the bed is very porous in these environments. It's made up of cobbles, stones, gravel, and sand. And as that water passes through with the sediment in it, it gets filtered out, in essence, by that bed, and we have an entrapment, and we remove sediment that way. Now, that's not to say it stays there. When you have a big storm, it'll move downstream again. But we applied this entrapment coefficients to the model, and we found that if we had a 300 milligram per liter slug, 40 kilometers downstream, we would have lost about 2/3 of that. This assumes no incoming sediments over that reach from a modeling standpoint. This is important information because we can determine what's coming in at different flows and such to the Athabasca from, for example, the Ells River. These are boundary conditions for the 1 and 2D models that I'll be speaking of. The 1D models, there's multiple models that were used. There's multiple parameters that we could look at. I have provided just 3 here for sake of presentation. We look at water levels relative to the ramps flows that we used here, which is in the green on the top. And then we used a model called Mike 11. And it predicted the flows fairly well for open water, but it was terrible for the under ice conditions. It suggested a lower level than what should actually or is actually there. So we started using models now that allowed us to look at the effects of that ice cover. If we look at suspended sediment, we see the ramp data in the dots, and the blue line is accounting for that ice cover. We represent the ramp data not too bad. And over the winter, where there is no suspended sediment concentrations, we show a very low concentration in suspension. And having worked on that river in the winter, over the last 3 years, we generally have anywhere from below 1 to 2 milligrams per liter. We're predicting a little bit too low here on the model, so we'll be working with that on suspended sediment, but we're pleased that it does show a lower value than if we didn't account for that ice. If we use a water quality parameter, example is simply using oxygen content, dissolved oxygen. We can see ramps data on the dots, and the blue line again is the model looking at flows. oxygen rather, moving through the system. And we can see that we represent that fairly well, and that during the ice period, which is that dip down on each of the peaks there, we see that we predict a lower dissolved oxygen concentration under ice, which we're pleased with because that's what should happen, because you no longer have the diffusion of oxygen down into the water from the air-water interface. It's sealed off. So from this, we know, and from the conditions that we know, that the Athabasca is a ice-dominated river. 6 months of the year or so, it's covered with ice, and that influences its flow, it influences its sediment transport, it influences the contaminant transport of natural substances moving down that system. One area that we do not know a lot about and is very difficult to model is during the breakup. This very short period of time is probably the most significant time of the year where we move huge volumes of sediment. The concentrations under here will be orders of magnitudes higher than at any other open water period. If we could run that video, please. This is an ice run on April 2013 below Fort McMurray, and you can see the intensity that's going down this system. These are 1 10-ton blocks of ice that are digging into the bed, mixing the sediment up, creating huge turbulence, and bringing sediment up into suspension. I should state no animals or humans were hurt during the making of that video. And this time of year is really important, but it's very, very difficult to model. So we know that people around the world are working this area. This is not included in any of our models because it's so difficult. The two-dimensional modeling, this is the EFDC model, which is the common platform between the province and the Environment Canada. Allows us to look at the two-dimensional over time and space of various substances. Here I'm using an example of total suspended solids, and if we zoom in on the steep bank and the L's, we can see that both of these rivers are bringing in large quantities of sediment potentially to the system, but if you look downstream by the color charts, you can see that these sediment concentrations are decreasing as we go downstream, likely due to that deposition and entrapment that I spoke of. We can link with this various substances. Here I've chosen, just for the sake of argument, phenanthrene, which is within the implementation plan. And again, we see that associated with that suspended solids, inorganic and organic fraction, there's an increase in phenanthrene where we have an entrance of the L's and the steep bank. But that also dissipates as we go downstream, again, likely due to deposition and entrapment. We can model sediment deposition in these systems. Zooming in on the steep bank, we see that the majority of sediment, if it's in the main stem, will rush through that system. Possible some entrapment within the sand wave dunes that are moving down that river, but that we have deposition occurring in the backwater floodplain areas and on the lee of islands. So I want to move finally into the last phase, and that is the hydrological modeling. We're dealing with huge data sets here. We're dealing with the entire Athabasca Basin. We're needing to look at topography, soil types, land cover, and we also need to look at climatic variables. Now, JOSM was never set up to be studying climate change, global climate change, but in this case, we needed to look at some of the climatic characteristics, precipitation, snowmelt, and such, so we had to look at some of the global climate models. Modelers use 6 different global climate models with 2 different downsizing techniques, so essentially 12 models were run for every scenario. When we're thinking about changes for the future, essentially driven by climate is the greenhouse gas. Currently, we have a greenhouse gas of about 2 watts per meter squared. But what we've done in the modeling here is gone to a 4.5, which we've termed a moderate increase in greenhouse gas, and 8.5, which we've termed as a high greenhouse gas. So don't want to get too hung up on the numbers, just that the work that we're doing is on moderate and high greenhouse gas scenarios. So the model needs to be accurate. We need to do some calibration and validation on known data, and the hydrologic model worked out quite well, being able to predict peaks in the hydrograph down in the lower Athabasca River, for this case at Fort McMurray. Precipitation-wise, we've looked at 2 different time frames, from 41 to 70 and 70 to 99, with moderate and high greenhouse gas. And we see that we have an increase, it's expected to have an increased precipitation from anywhere from 30 in one condition up to about 80 in the other. This represents a range of about 6 to 13% from the current rainfall conditions. And if we look at snow water equivalent, it's another aspect of water coming down to the Athabasca. We see that in the bottom right-hand corner that we have a high scenario of greenhouse gas in time, that we have an actual reduction in the snow water equivalent. This is in millimeters, so just like when we say we have 5 millimeters of rain, this is the amount of rain or snow melt equivalent. And it's from 0 to minus 100 millimeters, so it says we're losing about 80 to 90 millimeters in the headwater of water equivalents from the snow. That only represents about 5 to 10% of the current stock. And if we go to the near field, 41 to 70, say, of the moderate greenhouse gas, there's not too significant of changes in the snow water equivalency. All of that is to get to this type of a diagram where we are comparing against the current conditions, or our control conditions rather, 1970 to 2000 with these 4 scenarios. And we have all of the variability because each of those 6 climate models give hugely different results, and that's why we wanted to use them, was to look at that potential variability within those systems. And what we find is that overall, there's an increase in autumn, winter, and spring flow, and a relatively small decrease in summer flows. There's the largest increases in March, April, and May, and that the overall shift, there's an overall shift or an earlier rise, if you will, in the mean monthly hydrograph, and increases rather in peak flows, particularly for that scenario of high greenhouse gas. So this type of information is what would be tied back into the 1 and 2D models, as well as our flows that would be coming down that system. So finally, what we want to continue to be working with in the future in this regard is to evaluate and provide projections of the impacts with regards to land cover change that was spoken of a little bit with my previous speaker. We're working a little bit on that area right now. We hope to continue doing that, and the influence of land cover change on that hydrologic regime rather, and continue to look at the climate variability and its influence on water availability in the region, and also how that climate variability will influence water quality, sediment, and chemical substance transport. Thank you.
Any questions specifically for Ian? And then while we're waiting for that, if I could get John, if you wouldn't mind coming up, and George as well. I see a couple people maybe working there. Nope, they're going to their table.
We got one on the left side.
I have a question. Ian, can you successfully model that entrapment process that you referred to that occurs on the riverbed? And further to that, can you model the stochastic processes of storm events that affect the release of those sediments?
That's a really good question. We end up having to, with the entrapment, is to use some of the work that we're using in the flumes to test back with using that gravel bed, which we're doing, is looking at how well are we predicting the entrapment in that system. And I can't remember your last question. From a hydrology standpoint, from a sediment contaminant transport standpoint, looking at like extreme events and things like this, yeah, as long as we have the proper units for the storm event, the hydrograph essentially coming in, and everything's parameterized, we can provide a projection of what we may expect with a range.
Hi, just a question about how you're incorporating the climate variability. It's great to see that you are. I was just curious, across different components of oil sands monitoring, or perhaps it's across different Environment Canada or even Government of Alberta, is there a kind of standardized approach to selecting those scenarios and the way they're applied in a say a watershed or across media? And if not, should there be? You know, I'm not sure what the pros and cons are of that.
I think obviously there's a lot of pros to everybody approaching scenario building in the same way. I'm not aware of that being done. That said, I think is a real move afoot to try and have some more integration between some of these groups so that we can be doing things such as the scenario building or even other aspects of research that goes on.